Hello, quick video on differentiation and the full mathematical terminology we use for it. We looked at in the previous video creating a little triangle for our curve and finding the gradient of that, and we just talked about it being a gradient. What we're going to do now is use more specific mathematical language what we're here for a differentiation which creates a differential, which is sometimes called the derivative. For all practical terms purposes, this is the gradient or the rate of change. So if we wanted to know the acceleration of a body, or we wanted to know the growth rate of an investment, or we'd be looking at this gradient, this differential, this derivative. And again, this calculus was created by Newton and Leibniz, but the terminology we're going to use is the Leibniz terminology. If we were using Newtonian, we'd be talking about fluxions, but people don't. For whatever anybody says, we're using the German Leibniz terminology, and it works quite well. So let's have a look at the terminology. Okay. So remember our little triangle here that we created earlier, and we had a base we called H before, didn't we? Well, now we're going to call it something different, and we're going to call it delta x. So this first letter here is the Greek letter delta, which we're using in the term here as little, or a small change, yeah? And we've written the x beside it because it's telling us here that it's a small change in x. It's a small increase, to be precise, but it's a small increase, a small change in x. This is one term. It is not delta times x. It is just delta x. So that's telling us it's a small change in the x direction. And up here we've got delta y, which is a small change in the y direction. And therefore the gradient of this little triangle and of the white line that we've created is delta y over delta x. Yeah, so we've got a little change in y, a little increase to be in looking at the direction, and a little increase in y, delta x and delta y. And what we're interested in is what happens when we make this triangle smaller and smaller and smaller. So our little delta y is getting smaller, delta x rather, is getting smaller and smaller and smaller. Yeah, what we're interested in doing to find the differential, and this is the differential here, dy, no, I said d, not delta, dy by dx. Well, that is the limit. What's the limiting value of delta y over delta x as our little delta x tends to 0? And for all practical purposes, delta x is 0. So we write that mathematically as dy by dx equals the limit as delta x tends to 0 of the expression delta y over delta x. Okay, so that's what we're doing here, is we're finding our little delta y and a little delta x, and for our little delta x, and we're finding what the limit is as our little delta x tends to 0, as we did before our h tends to 0. Okay, let's work through an example using this terminology. We'll go back to our example of y equals x squared. So our first point we start off is at x, and therefore the y value there is x squared. And then we're going to move along an increase of a little delta x. So the x value of our second point, the one up here, is x plus delta x. And if that's our x value, then our y value is that squared, isn't it? Well, we know what our moving along is, it's little delta x. What we're interested in is finding out what the expression is for delta y. So what's our up for up over along? So our delta y is going to be the difference in our two y values. And the first y value is x plus delta x all squared. And the lower one, the start point is at x squared, isn't it? We can expand this bracket here using the grid method, and we get x squared plus 2x times delta x. Remember, delta x is one term. It's not delta times x, it's just delta x. And plus delta x squared. So that's the bracket. And remember, then we have to take off our original x squared because we're going to look at the difference. So again, you can see these two are going to cancel out. Yeah. So our delta y, our little up, is 2x times delta x plus delta x squared. Can you see how this looks like we were using h before, weren't we, where we had our delta x? So our gradient is delta y over delta x, our up over along. We've got our expression for the up. We've got x divided by the expression for the along, which is delta x. So our first term is 2x times delta x divided by delta x. So those two delta x's cancel out again. So we end up with our first term is 2x. Our second term is delta x squared divided by delta x. And that gives us, you know, a number squared divided by a number gives the original number. So that's plus delta x, isn't it? Now, we're going to take our idea that we had before. We're going to make this triangle very small. In fact, we're going to make it infinitely small. So we're looking at what happens as delta x tends to 0. So our differential, our gradient, dy by dx, is the limit as delta x tends to 0 of delta y by delta x. Well, our first term remains at 2x, but our second term, which was delta x, becomes 0. So therefore, dy by dx, our differential, there we are, is 2x. Yeah. So what we've done again is prove that for the curve y, function y equals x squared, dy by dx, the differential is 2x. We could do the same sort of thing with y equals x to the n by putting those into the y values and by expanding the first bracket here. That's the differences. There's our upper y value and that's our lower one. We need to expand this bracket, which we can do with binomial expansion. And again, we find that we've got an x to the n term on both of these that cancel out, and we end up with this second term here. There we are. That's our biggest term, isn't it? A term and multiple of delta x. Then we find our gradient here, dy by dx. We've got the terms we just had divided by delta x. So we find again that we get our first term, here it is, n times x to the n minus y, and that's not a function of delta x, is it? All the other terms are functions of delta x in our binomial expansion, and therefore when we find the differential, which is the limit as delta x tends to 0 of what we had above, dy by dx, we find that we've got this term here and all the other terms go to 0 again, don't they? And therefore dy by dx, therefore we are just left with dy by dx is going to be n, the first term, and therefore once again we've proved that for the function y equals x to the n, the differential dy by dx, which is the gradient, is n times x to the n minus 1. We can adopt this approach just to point out for any other function of x. So here we can do it for y equals 1 over x squared, and if we go through exactly the same method, we will find that the differential dy by dx in this case is going to be equal to minus 2 x to the power 3. I'll leave you to think about why that might be so, how that follows the pattern we looked at for positive powers. And we can do exactly the same method for sines and cosines and things like that. And if we do that, we find that for y equals sine of x, we can find that dy by dx equals the cos of x, just by going through this same little difference triangle. So here's my summary of using the Leibniz and the full differential calculus terminology. The differential, or the gradient, or the rate of change, we can find using differentiation. Differentiation means creating one of these small different triangles, which has got a base of delta x, a small change in x. Remember, that is a single term, that is not delta times x, it's delta x, and a vertical small change of delta y, and therefore the gradient is y by delta x, and the differential is the limit dy by dx, that's the differential, is the limit as delta x tends to 0 of delta y over delta x that we calculated there. And we can use that to find the general differential of function y equals x to the n, to show that dy by dx, i.e. the gradient, is n times x to the power n minus 1. I hope that that's useful as a specific proof, particularly if you're a further mathematician and you need to be able to carry out differentiation of any function, and therefore you need to be mathematically accurate.